All right, so we're going to look at the chain rule in 2 or 3 variables. And we're going to start with just by laying out the definitions. If we have a function, let's say it's of f of x, y, but our x is actually a function of another variable and y is also a function of another variable, what we end up with is our derivative with respect to t is actually not a partial derivative, it's actually just an ordinary derivative. But we find the partial derivative for w with respect to x, and we multiply by the ordinary derivative for x with respect to t. You can think of the dx's canceling, quote unquote. And then same thing we have, because we have another variable, the total change for time is going to depend on both x and y. And so the second component is del w, del y, the partial derivative of w with respect to y times the ordinary derivative of y with respect to t. Now, if we have a three-dimensional case, then we have exactly the same thing, but we have a third component, the partial derivative for w with respect to z times the ordinary derivative for z with respect to t. Now, if our substitutions are going to be themselves dependent on more than one variable, let's say 2 of them, then we would have 2 partial derivatives for w, one with respect to t and one with respect to s. Consequently, if our functions were themselves based on 3 variables, then you can imagine there would be a third version of this, but we're going to stick with just this in order that's sufficient for the generalization, I think, to be clear. So our partial derivative for w with respect to t, again, still partial because there is another variable out there. We would take the partial derivative for w with respect to x and multiply by the partial derivative of x with respect to t. And then plus we would add on the partial derivative for w with respect to y, and then multiply by the partial derivative for y with respect to t. And then we would repeat exactly the same thing for the partial derivative for s, but we would replace our partial derivatives for t with partial derivatives for s. And then in the three-dimensional case, of course, if your original function was of 3 variables and x, y, and t were also in terms of 2 variables, then you would add on your third component with your partial derivative for z and your partial derivative for t in the t derivative, and the partial derivative for z times the partial derivative of z with respect to s in the s derivative. All right, so let's actually look through an example of each of these. So we're going to find dw dt, and our original w function is xy plus xz plus yz. And our 3 chain rule components are x, y, and z are defined in terms of t as x is t minus 1, y is t squared minus 1, and z is equal to t. Now, I find it helpful to basically make a nice table out of this data so that it's easier for me to work with and make sure I pull in all of my components and not forget things. So the partial derivative of w with respect to x and the partial derivative of w with respect to y, I put those in one column, and then the partial derivative of x with respect to t and the partial derivative of y with respect to t, I put in another column. And again, the z is also there, but it's folded over onto the next page. And then each of these, I take the derivative. So the derivative of w with respect to x, I get a y, I get a z, and I get a 0. And the partial derivative of w with respect to y, I get an x, I get a 0, and I get a z. And then for my z derivative, I get a 0, and then an x, and then a y. And my partial derivatives for x with respect to t is just a 1. Partial derivative of y with respect to t is a 2t, and partial derivative of z with respect to t is also 1. Now, one thing to kind of keep in mind that's very important, if you are ultimately going to plug values in and you're just going to get a number in the end, then you may not need to worry about this because you can just plug in values and all of your various derivatives will go away. Your various variables will go away. But if you're finding a derivative of w with respect to t, it should not have x, y, z, and t in the final answer. It should just have t in it. So before I do any substitutions into my chain rule formula, I'm going to do my replacements in my derivative. And so y is t squared minus 1 and z is t. And so I get my partial derivative for x with respect to t. My partial derivative of w with respect to x, but in terms of t. And then I do the same thing for the partial derivative of w with respect to y to make it in terms of t. X is t minus 1, z is t, I get 2t minus 1. And finally, for the partial derivative of w with respect to z, I want it in terms of t for my final answer. So I do my substitution, t minus 1 and t squared minus 1, and I get this. And now I can apply my formula. So using the values from my table, my del w del x in terms of t is this. My del x del t is 1. Del w del y in terms of t was this. My del y del t is this. My del w del z is this in terms of t. And then dz dt in terms for my table is 1. And then I can do my simplification, FOIL everything out, combine terms, and I get this. Now, it is certainly possible to find that you can verify this by other means, by actually switching the order of operations, plugging in your t's first, and then just finding your derivative with respect to t. Now, I want to caution you is that if someone's asking you to find the derivative and the function is in terms of x and y are themselves in terms of another variable, they're actually asking you to show that you know how to use the chain rule. They are not asking you to plug in all of your substitutions and then turn it all into one variable and then find those derivatives directly. But it is useful as a check at the end. If you just want to make sure that you did all the components right and doing it by another means with different sort of algebra pieces, if you can get the same answer, there's a good chance that you did all the algebra correctly and that you applied both rules appropriately. So simply as a check, I just want to make this clear, this is simply as a check, I can substitute x is t minus 1 and y is t squared minus 1 and z is t into my original problem. And again, doing all the algebra, FOIL everything out, and I can get an expression for w in terms of t. If I take that derivative just normally with respect to t, I should get the same answer that I got from my chain rule. So for this particular example, everything did work. But again, I just want to caution you, if you see a problem like this, don't do this except as a check. You can't circumvent applying the chain rule this way. The whole point of having the chain rule is to apply the chain rule. Otherwise, your professors would not be asking you this question on an exam. They want to see the chain rule. They want to see you work through those formulas and that procedure. And partly this is not so much for these cases where the algebra is relatively simple and you could actually work around it. It's for those cases where maybe you don't know what you know that the function x is dependent on other variables, but maybe you don't actually know what it is. And so it's important to be able to apply the chain rule appropriately and not like go around it. I went around it here merely to check my answer. And as I noted earlier, you do want your final answer to be in terms of a single variable. If your x and y are functions of a single variable. You should not have all 4 or 5 variables in your problem when you're finished, in most textbooks. Now, the other thing that I would mention is, before we move on to the partial derivative case, is that sometimes they will give you values for these problems to evaluate the derivative at. Sometimes they will give you values for x and y and z, and sometimes they will give you the value for t or t and s. You want to make sure that if they give you x, y, and z, that you find the corresponding value for t or s and t in order to plug them in, because you'll need them for this. If they give you the values for s and t, then you will use your formulas for x, y, and z and those values to find the corresponding values for x, y, and z. And then again, if you're going to get a constant at the end, you can just go ahead and substitute those constants into your partial derivatives before plugging them into the formula. Or you can just wait until you've simplified everything and then plug your s and t values in one time at the end. But do be careful about whether they're giving you x, y, and z, or whether they're giving you t or s and t for those constants. All right, so let's look at our second example. This is for the case with the partial derivatives, and we have a function of both s and t for our x, y, and z variables, and our w is also in terms of 3 variables, x squared, y squared, and z squared. And we're going to find the 2 partial derivatives, and as I did before, I'm going to make a table of my values so that all of my derivatives, so that I have all the pieces that I need to just plug things in together. So my partial derivative of w with respect to x is just going to be 2x. My partial derivative of w with respect to y is just 2y. My partial derivative of w with respect to z is 2z from up here. My partial derivative of x with respect to t is sine s. My partial derivative of y with respect to t is cosine s. My partial derivative of z with respect to t is 2st. Partial derivative of x with respect to s, that's the derivative of this with respect to s, is going to be t cosine s. Partial derivative of y with respect to s is the derivative of this, and the t is going to stay the same, but cosine s will become minus sine s. And then the derivative of this with respect to s is going to be t squared. And again, before I plug everything in, my final answers should have only s and t in them. And so again, if I'm not substituting in actual values, I want a function. It should be a function of s and t. And so I'm going to substitute 2x here, and I'm going to replace x with t sine s. My 2y, I'm going to replace the y with t cosine s. And then 2z, I'm going to replace with st squared. And then I'm going to stick everything into my chain rule. For the partial derivative for t, I'm going to pick my 2t sine s times sine s, and then 2t cosine s times cosine s, and 2st squared times 2st. Notice the advantage of these tables is that you're multiplying across here. And for the s derivative, I'm going to multiply this one by that one, and this one by that one, and this one by that one. And so it's a little easier to stay organized. And once you do all this multiplying, then you do some simplifying. We've got sine s squared and cosine s squared, and sine squared and cosine squared reduced to 2t, just the coefficient out front. And we get a much simpler expression after the simplifying. And then we do the same thing for the partial derivative for s. And again, we can just use the table. Del w del x is 2 sine t, or 2t sine s. And then del x del s is this guy over here, t cosine s. And then del w del y is this guy, and then times del y del s is that guy, and then del w del z times that guy, del z del s. Now, when you do this, you find this is the negative of that one, so that term cancels out completely, and then you just combine your t squareds and you get this. And as we saw before, it is certainly possible to verify your answers. If you plug your substitutions into the original variables, you're going to get some sine squareds and cosine squareds, and they're going to simplify, and you're going to end up with some kind of a polynomial in s and t. And then when you take the derivative for t, they both have s's in them, but when you take the derivative for s, there's only one expression with an s, and you end up with just one component left.